So our project it started very recently, November 2022. So let me start the background and advantages of our R&D. And again, there are various modalities for quantum computing, including superconducting qubits, trapped ions, and then our cold atoms, which is laser cooled down to the temperatures almost 0 Kelvin. And this is our machine, and inside this vacuum chamber, there is a neat array of many cold atoms, rubidium atoms here. And these atoms, each of them is moved atom by atom with movable optical tweezers, which is tightly focused laser beams that grabs and moves a single atom. And each of these atoms serves as a qubit. And this qubit is manipulated with another laser beams. And this manipulation is referred to as a quantum gate. And as you may know that the maximum number of the qubit is something like 100 to 1,000 qubits in a single array for superconducting qubit and trapped ions. Whereas in cold atoms, so it can be pretty much easily scalable above the 10,000 qubits, and coherence time is longer than the superconducting qubit by 4 orders. And also the qubits movable during the calculation, and this might be a game-changing in 2-qubit gates. And for this reason, it is quickly emerging among the most promising modalities for the quantum computing. In our computer, the lots of atoms are assembled one by one with a movable optical tweezers to make any arbitrary array of rubidium atoms. And each atom serves as a high-quality qubit on the ultra-fast time scale. And each atom also can be moved arbitrarily during calculation as necessary. And 2019 November, so we succeeded in trapping a single atom in a single tweezers. And then this is scaled up to 800 atoms in January 2021. And this 800 atoms is one of the largest arrays of cold atoms. And so for these 800 atoms, we can initialize these qubits simultaneously. And as we load the atoms from the magnetic optical traps into our tweezers, so its temperature is not very low. It's something like 50 microkelvin. So there is a thermal motion in the tweezers of the atoms. And so the atom position uncertainty is pretty large, 100 nanometer. And so therefore, we operate additional cooling down to the ground state of the tweezers and suppressing this atom position uncertainty down to 25 nanometer. And we can do so all over the 800 atoms simultaneously. And we have also succeeded in making world's shortest atom pair distance, something like 1 micron. And if we can excite both of these nearby atoms to the Rydberg, then this large distance between the positive and negative charge induces a strong dipole moment and leading to the strong dipole-dipole interaction. And then will be a driving force of ultra-fast 2-qubit gate. But however, here is a key issues to do so as follows. So in previous works, the people have been using continuous wave lasers for the Rydberg excitation, so that they had a so-called Rydberg blockade. Therefore, they were not able to bring 2 Rydberg atoms closer than typically 5 micron. Therefore, we replaced this continuous wave laser by ultra-fast pulse laser for the first time. And then we can circumvent this Rydberg blockade. That is, that we excite the neighbor atom faster than the Rydberg interaction. Then we can bring these 2 Rydberg atoms closer than 1 micron. And actually, this is a resource for an ultra-fast 2-qubit gate faster by 2 orders than before. And by using this complete new idea, we can excite both of these 2 nearby atoms around 1 micron distance to the Rydberg level simultaneously. And then this short distance leading to the strong Rydberg interaction. This is the driving force of ultra-fast 2-qubit gate. And by using this ultra-precisely controlled atomic distance, so we investigate the interaction dynamics between 2 Rydberg atoms in 2 Rydberg atoms in these 3 Rydberg levels. You know that there is an accidental degeneracy so that there can be energetically identical between the 2 atom state, 45P and 41F, and 43D and 43D, due to the dipole-dipole coupling. And this is, so this kind of oscillation leads to the oscillation which is referred to as a Feldstein oscillation. And this shows our experimental observation of this kind of a Feldstein oscillation. When we change the atomic distance from 4.9 micron to 1.5 micron, so we have a population oscillating between the DD state and PF state almost 4 times at 6.5 nanoseconds, delay at 1.5 micron distance. That means that the one oscillation takes something like a 1 point something nanoseconds. And now we change the delay from 6.5 nanosecond to 2.3 nanosecond. And then the number of oscillation reasonably decreased. And then we convert the abscissa from distance r to jt, which is the interaction strength j multiplied by time. Then we have a damping of the oscillation. And we compare these experimental results with a theoretical simulation. So this dashed curve, so where we incorporated entanglement with emotional degrees of freedom. And that is the 0-point fluctuation of the atomic position in the tweezers. All right, and then this dashed line agrees pretty well with our experimental observation. Thus, you can see here is that our damping is almost dominated by the 0-point quantum fluctuation of the atom position after extra cooling that I have shown you right now. And after this result last year, so we have an additional suppression of the atom position uncertainty well beyond the standard quantum limit down to the 10 nanometer by squeezing the atomic wave function in the tweezers. And actually, the sign of the DD state is flipped from plus to minus within this one oscillation between 43D, 43D, and 45P, 41F. And this sign change completes in the time scale of 1 nanosecond, so that this should be a promising resource for an ultra-fast 2-qubit gate on the 1 nanosecond time scale. And for your reference, the fastest controlled gate is demonstrated by the Google AI with a superconducting qubit. And here, this is a control Z gate. And to recap the control Z gate, here is a cartoon to show you the CZ gate, how it works. You have a control bit and a target bit, and you create a 0+1 superposition in a target bit. And if the control bit is in 0 state, so nothing happens to this superposition. Whereas the atom 1 is in 1 state, then this 0+1, the sign of this 1 state flips from plus to minus in nanoseconds. And this is a CZ gate, and one of the most important quantum logic gates for quantum computing. And actually, there are many 2-qubit gates. And in particular, for this group of 2-qubit gates, referred to as the control gates, which is a conditional 2-qubit gate where the operation on the target bit is determined by the state of the control bit, so that they are entangled. So why these control gates are particularly important? Because this is entangling 2 qubits, which is at the heart of the quantum computing. And it can be converted to any other 2-qubit gates when combined with a single qubit gates. In this example, this CZ gate is combined with 2 Hadamard gate that changes 0 to 0+1 and 1 to 0-1. This makes a C0 gate, and 3 C0 gates makes a swap gate. So in this way, the control gate is origin of any other 2-qubit gate. So this is one of the most important gates. So making this CZ gate ultra-fast should be exciting. Then why you need an ultra-fast gate? Because the fidelity of quantum gates degraded easily by the external noises, including motional coupling or laser phase noise. And the time scale of these noises is no faster than 1 microsecond. So that if you could have a nanosecond gate, so you can be free from those noises. However, so it is well known that 2-qubit gates with cold atoms are very slow, ranging from sub-microseconds to 1 microsecond. So comparable to the time scale of this external noise. However, our driving force interaction is much, much faster than the Rydberg lifetime, hundreds of microseconds, and also much faster than the conventional slow Rydberg blockade, whose time scale is sub-microseconds to 1 microsecond. So that we should try to make this interaction driving force of the ultra-fast 2-qubit gate. And therefore, we have experimentally investigated whether this DD gate is the DD state is really phase flipped by pi in nanoseconds. And here, so we create a 1-to-1 superposition of the zeros and 1 state in target bit, and also another superposition of these 2 cases. In one case, the control bit is in 1 state, and the other, the control bit is in 0 state. And what we observe is the superposition of these 2. And then we employ the time domain Ramsey interferometry with attosecond precision to visualize the temporal oscillation of this 1 state relative to 0 state. And then make JT 0, pi, and 2 pi by changing the distance between 2 atoms. And at JT equals 0, so these 2 start oscillating in phase. The contrast of this Ramsey interferogram should be very clear. But at JT equals pi, if the CZ gate operates properly at JT equals pi, so this phase flips by pi. So this superposition destructive interference, so that this contrast will be suppressed. And then at JT equals 2 pi, coming back from the PDF stage second time, so these becomes in phase again. so that the contrast will revive. And these are the experimental results. So red one is for a pair of atoms, and the gray one is for single atoms. And we have observed that the contrast changes exactly what we expected. And this contrast and phase has been compared with the ab initio calculation. And these dots are experimental results, and the solid lines are calculations. And for both contrast, red one, and phases for blue one. And they agree very well between the experimental results and theoretical simulations. And demonstrating that our CZ gate is actually completes in just 6.5 nanoseconds in our case. And however, the conditional phase, what we observe here is 1.17 pi instead of pi, what we want. This arises from additional coupling channel in addition to the 45P and 41F that we are considering now. But this conditional phase can be finely tuned by external electric field. And this is what we are elaborating right now. And here we have thus demonstrated the fastest record of the control gate with cold atoms. And this is working in just 6.5 nanoseconds at 2.5 micron atomic distance. And for your reference, the fastest controlled gate by superconducting qubit is 15 nanoseconds demonstrated by Google in 2020. And this is also the first quantum speed limit gate with cold atoms, and 100 times faster than any other control gate with cold atoms so far. And the speed limit gate is the gate whose gate speed is solely determined by the interaction strength. And this is the first quantum speed limit gate with cold atoms. And actually, there are theoretical proposals 20 years ago about fast quantum gates for neutral atoms, authored by the theorists including Peter Zoller or Sirac and Lukin. And in this paper, they proposed two schemes. One is this ultra-fast gate, speed limit gate, and the other is slower Rydberg blockade gate, for which I am not going into too much details. And after this paper, so only this slow conventional Rydberg blockade gate has been implemented because this is easier. But no one has been able to make this quantum speed limit gate realized because that no one has been able to bring these two Rydberg atoms closer than 5 micron. And this time, we have implemented this quantum speed limit gate with cold atoms for the first time by incorporating a completely new idea in which we combine ultra-fast laser and quantum technologies for the first time. And this has been highlighted by the cover page of the Nature Photonics October issue 2022, and highlighted by more than 200 news outlets in Japan, US, Europe, and China. And these are the guys who made this possible. And this is part of the review report at the Nature Photonics. The results presented here open the possibility of boosting the time scale of individual gate operations by multiple orders of magnitude, which indeed is a major new concept and highly promising. And so these outstanding advantage in the development of cold atom-based quantum computers will be fully utilized in the global development race. And here we have a report of the progress of our project, just started in November 2022. And we have 4 R&D themes: scalable platform for quantum computing, high coherence, high fidelity quantum gates, and quantum error detection correction architecture optimized for cold atom systems, and highly stable, high power, and compact lasers. And we set up a R&D unit system where there are a cold atom unit, a hardware development unit, and a laser development unit. There is not necessarily a one-to-one correspondence between these units and the themes. For example, cold atom unit is covering themes 1, 2, and 3. And also, there is not necessarily a one-to-one correspondence between the PIs and R&D unit. For instance, I myself, as a PIs, belongs to both the cold atom unit and hardware development unit. All right, this is a strong lineup of the PIs, and myself, I also take responsibilities as a PIs, and I belong to cold atom unit and hardware unit. And Sylvain de Lezeluc from IMS, he belongs to all the units, cold atom, hardware, and laser development. And Takafumi Tomita from IMS too, and belongs to cold atom hardware. And Professor Yoshiro Takahashi at Kyoto University, cold atom unit. And Dr. Takeshi Fukuhara at RIKEN, a cold atom unit. And Professor Takunori Taira from IMS, a member of the laser development unit. And Dr. Chihiro Yoshimura from Hitachi Company, he is a member of the hardware unit. And finally, Professor Keisuke Fujii at Osaka University joined us from the Kowashi project, who gave a presentation this morning. And he will contribute to the theoretical development of the fault-tolerant scheme dedicated to the cold atom system, where you can move the qubit arbitrarily during the calculation. All right, and this is my responsibility as a PI, which is the integration of cold atom quantum computer hardware. And as I already shown you today, that we developed the first generation machine starting in 2019, and now developing the second generation machine in collaboration with companies to develop the a well-integrated system, including a control system, laser cooling, and vacuum chamber and surrounding optomechanics. And this is the responsibility taken by the Sylvain de Lezeluc. And as I have shown you, we have developed the ultra-fast gate, but we need to improve the performance of the ultra-fast gate. So there is several directions to do so. One of them is suppressing the quantum fluctuation of an atom position in the tweezers. So to do so, we have squeezed the atomic wave function in the tweezers, and then go beyond the standard quantum limit and reduce the atom position uncertainty by 6 dB. And another direction will be ultra-fast spin resolved excitation. Our ultra-fast lasers will not resolve the qubit state in this long-lived hyperfine qubit because the bandwidth is broad. So that we create a longer pulse whose bandwidth is smaller, 1 gigahertz. Then this is incorporated into this excitation scheme, and then we can execute the spin resolved excitation to intermediate state with a fidelity 90% at the moment. And this is another responsibility by Sylvain de Lezeluc from IMS. And this is a system for the noise cancellation of the diode laser for conventional Rydberg blockade gate, which we will also implement in parallel to our ultra-fast gate. And as shown here, so we can suppress the phase noise of the diode laser by 30 decibel, so more than 2 orders in this 0.1 to 1 microsecond time scale. And this is the responsibility by Takafumi Tomita. And as I told you, we are developing slow Rydberg blockade gate. And for this, we are setting up the laser system to do so, including the laser source and the frequency locking system. And also, the Takafumi Tomita is elaborating for another responsibility towards the non-destructive measurement for a mid-circuit measurement. And so far, we have been using the destructive measurements, so in which we first shine a push-out beam to push out the atoms from the tweezer in one of the 2 qubit states. And then we shine the imaging beam to make the remaining atom fluoresce to collect the photons. So this is destructive in the sense that we lose the atoms depending on the state. And instead, we are implementing the non-destructive measurements where we use the push-out beam in the non-destructive measurement for imaging by optimizing the timing, duration, and trap width, not to push out the atom, but to make the atom fluoresce down to the original qubit state. All right, and this is a preliminary result where the signal from the one state is pretty much distinguished from the background, this gray peak. And this is the responsibility by Professor Yoshiro Takahashi at Kyoto University. They are developing the cold atom computer with ytterbium atoms, having these advantages. And they already performed the basic performance, including optical qubit and single photon Rydberg excitation. And more recent achievements include trapping single ytterbium atoms with more than 100 sites, efficient parallel rearrangement of a 2D atom array, and Raman sideband cooling, and nuclear spin Rabi oscillation, and high fidelity single qubit X gate. And so another option to use 2-electron system is using the strontium atom. And this is the responsibility taken by Dr. Takeshi Fukuhara at RIKEN. And in strontium atom, there are also metastable state turret P0 and turret P2, which will be useful for non-destructive measurement in mid-circuit measurement. And compared to ytterbium, one specific feature is that they have a narrow cooling line to turret P1, whose line width is only 7 kHz, and which will be useful for atom cooling, such as Sisyphus cooling, with shallow potential that leads to less heating and more tweezers with less laser power. And this is the responsibility taken by Professor Takunori Taira from IMS. And he invented revolutionary room temperature bonding for new photonic function. And that leads to the functional power laser by tiny integrated DFC chip. And this allows for the development of a trap laser that can trap more than 10 atomic qubit, and also the stable pulsed excitation laser, leading to the stable Rydberg excitation. And finally, this is a responsibility taken by the Chihiro Yoshimura-san at Hitachi Company. And they are developing the quantum OS, which efficiently moves qubits to execute complex quantum circuits. And this part of this project is performed in collaboration with the Moonshot Mizuno project, where we develop this quantum OS, both for these movable atom qubits and silicon qubits. So that we have a tight collaboration with the Mizuno project. And that's it. And sorry for the troubles in my presentation, and thanks for your attention.